Okay, I will start sharing my screen. Okay, so can you see my screen? Can you hear my voice?
Yes, Doctor.
Yes, Doctor.
Okay, thank you for the response. Okay, so last week we have learned up to this slide. Okay, we have stopped until this slide, and then we haven't gone through this slide yet. Okay, so before we proceed, maybe we can have we can do some refreshment what we have learned in the previous week. Okay, so what you have learned actually is about the formatting process in order to produce digital signal. So from analog, you want to produce a digital signal. First of all, you need to do the formatting process. So formatting process is done within the analog to digital converter. Okay, so I think you might be familiar with the words ADC. ADC. So ADC is the analog to digital converter, which do the process of conversion from analog signal into a digital signal. Okay, and this process to transform the analog signal into a digital signal, it involves at least three processes, which are the sampling process, and then quantizing process, and the last one would be encoding process. Okay, so we have learned up to quantizations. Okay, so first we have learned about sampling process. So we take sample from the analog signal, we change it from a continuous time signal into a discrete time signal, which is what we call as the pulse amplitude modulation signal. And then we do the quantization, which is a process of rounded up the sample value to the nearest quantized level. Okay, so maybe we can refresh again what we have learned. So imagine that you have an input analog signal. Sorry, you have an input analog signal, which is, for example, here is a sine wave. Okay. Okay. So this is your input, for example, VMT. Okay. And then in order to convert this into a digital signal, first of all, you need to do a sampling process. Sampling process. So what happened in the sampling process is that it will convert continuous time signal, the analog is a continuous time signal, into a discrete time signal. Okay. Okay, so this is a this is a discrete time signal. So for example, NTS, so from TS to TS, TS is a sampling time, 3TS, 4TS, 5TS, 6TS, and so on. Okay, so when we sample the signal. Okay, we sample the analog signal by using based on the Nyquist theorem. Based on the Nyquist theorem, said that the sampling rate must be more or equal than 2 times the modulating signal frequency. Okay, Nyquist said that the sampling frequency must be more or equal than 2 times the frequency of the input. Okay, the highest frequency of the input. Okay, so this is a minimum Nyquist rate. Okay, sorry. That means the minimum sampling rate would be Fs equal to 2 FM. Okay, so this is the minimum. But in practical case, we sample more than 2 FM. Okay, remember FM is the highest, is the maximum input frequency. Okay, FM is the highest input frequency. So if you sample less than 2 FM, what happens is that the sample symbol will be overlapped in the frequency domain, which is what we call as the aliasing phenomena. Okay, and when we sample, we produce a signal what we call as the PAM signal, pulse amplitude modulation signal. Okay, so PAM signal is still an analog. Okay, when we do the sampling process, the way we sample is that, remember we have 3 types of sampling process, which is impulse sampling, natural sampling, and also the flat top sampling. So the way we do the sampling process is by multiplying the input signals with the pulse train. Okay, that is for the impulse sampling and also the natural sampling. But for the flat top sampling, instead of multiplication in time domain, we also do the convolution in time domain with the pulse train function. So sampling involves at least 2 signals multiplication process in time domain. Okay, and remember, the more we sample, okay, the more we do the sampling process, that means we can get many samples, the better would be the output. Okay, because we take many samples, so we can produce more accurate output. Okay, but there's a drawback about higher number of sampling. Okay, of course there's a give and take between the sampling rate and also the bandwidth requirement. Okay, so if you sample a lot, that means you need bigger bandwidth to accommodate the sample values. Okay, and after sampling, we can do the quantization. Okay, so quantizations. Okay, so I put here quantizations. So quantization is the process of rounded up the sample value to the nearest quantized level. Okay, so since we have many samples which have a variation of values, so we need to minimize the range of sample values. So that's why we do the process of quantization. We round it up to the nearest quantized level so that the range of quantization is not too big. Okay, so what happened? So when we do the quantization, for example, here I'm using a 4 level of quantizations starting from Q0, Q1, Q2, and also Q3, for example. Okay, okay, so this is still voltage versus NTS. So I rounded up the sample value to the nearest quantized level. Okay, so this is at TS, 2 TS, sample time, 3 sample, third sample time, 4th sample time, 5th sample time, and 6th sample time. So this is, in my example, I'm using 4 level of quantizations. And remember, the number of levels of quantization is equal to 2 power of n. Okay, n is the number of bit used in the system. So in this example, in my example, I'm using a 2-bit so that I can produce 4 level. Okay, so this is 4. Okay, in my example, I'm using 2-bit. Okay, so that means each level, okay, each level will be assigned with a 2-bit values. Okay, but in this example, this Q0, Q1, Q2, and Q3 is still in the form of voltage, but a limited amount of voltage. Okay, so when we do the quantization, we are actually rounded up the sample value to the nearest quantized level, Okay, so that rounded up process means that we are actually creating an error actually, because we increase or decrease a little bit of the sample value just to make it achieve the nearest quantized level. Okay, but that rounded up process, the error process produced through this quantization level is very small. Okay, it's very small, and it can be corrected later, no problem. There's no issues about the error process in this quantization. Okay, so if you see from here, again, as I mentioned earlier, that the more the quantization level would be better. Okay, if we have many quantization levels, that means the rounded up process would be very small, and the error that we produce would be very small, which is better. But if we go through if we use a higher levels, many levels of quantizations, we might need a wider bandwidth. Again, so that means here bandwidth always be the one of the constraint in the digital system. Okay, so we might need to consider as well the bandwidth limitations. Okay, and here we can see from here is that the resolution or the step size is the distance between each quantized level. Okay, which is what the resolution is a step size for each of the resolution is the step size or the distance between quantized level. Okay, so we have seen about this. Resolution is a Vmin, or it is a distance between the step size, the ladder size. Okay, so in my example, I'm using the uniform quantization. That means each levels has the same distance. You might see later that in the real world, we might also use a non-uniform quantization where each levels are different. Okay, so there's also possibility that we use a non-uniform quantization where each levels are different. So that one you might see later about that issue. And we have seen about quantization error. Okay, when we do the sampling process, when we do the quantization process, we will rounded up the sample value to the nearest quantized level. So when we do the rounded up process, we are creating an error. So this is what we call as a quantization error or quantization noise. Okay, so the quantization error is measured as modulus sample value minus the quantized value. Okay, so this is how much we increase or decrease the amount of the sample to the nearest quantized level. And according to this, the maximum quantization error is resolution divided with 2. Okay, so quantization error is equivalent to additive white noise. Okay, the word white here is not color. Okay, white here means that it is distributed across the entire frequency spectrum. That means regardless of the frequency that you used, the noise still happen. Okay, so this kind of noise, the white noise, is not depending on the frequency. Regardless of the frequency, it still happen. Okay, so that's why it is called as the white noise. distributed across the entire frequency spectrum. Okay, and QE is also called as the quantization noise. So QE and QN is the same. Okay, and from this example we have seen that, for example, here this is using 8 levels of quantizations. So that means it is using 3 bits, 2 power of 3, so you're gonna get 8 levels starting from minus 3.5 until 3.5 volt. Okay, so that means we're going to have 8 levels, and according to this example, the resolution or the step size is equal to, if you see from here, the distance between each level is 1 volt. Okay, the distance between each level is 1 volt. Okay, and if you see from here, 0 volt is not considered as the quantization level. Okay, 0 volt is not considered as the quantization level. Okay, and if you see from here, okay, so this is the quantized level is divided equally, positive and negative side. So it is like a folded binary, which is centered at x-axis. Okay, in this example. And according to this example, you can see that the resolution is the same, 1 volt. Okay, or the step size, the distance between each level is 1 volt. Okay, and this is the code number which you will see later in the third process of formatting, which is the encoding process. Okay, so the code number that we will give starting from the lowest quantized level to the highest quantized level. Okay, so we will see about this in the third process later after quantization. Okay, and from this you can see up to these 2 lines. Okay, so when we sample, we get 1.3 volt, and then we do the quantization, the nearest quantized level would be 1.5. So that means we rounded up the value for about 0.2. And then, for example, the second sample is 3.6. So the nearest quantized level is 3.5 volt. So therefore, the quantization error is 0.1. Okay, the difference. And then, for example, here the sample value is 2.3. And we rounded up during the quantization to 2.5 volt. That means the quantization error is 0.2. And so on. Okay, so we're going to see the third and fourth line later. Okay, the third and fourth line is regarding the encoding process after the quantization. Okay, and we have seen about this example, so let's go through this example. We have gone through this. Okay, this is based on figure 6, okay, which is this one. Okay, and based on this figure, figure 6, we can find that the resolution, as I mentioned earlier, we can see from here that the resolution is equal to 1 volt in this example. Okay, the distance between each quantized level. Okay, and then what? The maximum quantization error. So the maximum quantization error is equal to resolution divided with 2, or half of the resolution. So if the resolution is 1 volt, that means the maximum quantization error is 0.5 volt. Okay, so maknanya quantization error yang maksimum adalah separuh daripada nilai resolution. Okay, and then what? The last one, this is supposed to be C. So quantization error for sample 1, 2, and 3. Okay, where is sample 1, 2, and 3? So this is sample number 1, this is sample number 2, this is sample number 3. So we have 1.3, 3.6, and 2.3 volt. Okay, which is this one, the sample value. first, second, and third sample. So the first sample is rounded up to 1.5 volt, and based on this, the rounded up value, which is the error, is about 0.2. Okay, so we minus both of this. Okay, so sample value minus quantized value. So we put modulus to avoid the negative sign. Okay, and then sample value 3.6, we rounded up to the nearest quantized level 3.5. Okay, this one rounded up to 3.5. And the third sample 2.3, we rounded up to the nearest quantized level 2.5 volt. Okay, and if you see from here, from 3.6 becomes 3.5. So the rounded up value would be, so the rounded up value is 0.1 volt, the difference. Okay, perbezaan antara sample dan quantized level. And then here 2.5 sample value, 2.3 volt sample value, we rounded up to the nearest quantized level, which is 2.5. Okay, above here. So that means the quantization error is 0.2. Okay, and then what? We have seen about this also, example 6.4. Okay, example 6.4. This is about the quantization process. So this example is taken from the Frenzel's book. Okay, Frenzel's book. I have shared it in the author. You can go direct. You can see directly from the book if you want. No problem. Okay, so let's read this. The voltage range of AD. AD here is the ADC, analog to digital converter. Okay, that use 14 bit. You see that the number of bit is 14. N is equal to 14. So this ADC use a 14-bit number, and it has a range from -6 to 6 volt. So whatever sample that you get, it will be rounded up to the nearest quantized level between -6 to 6 volt. Okay, so these are the range of quantization levels. Okay, the range of quantization level from 6 volt until -6 volt. Okay, and then what? Find the number of discrete level binary code that are represented. So by using the 14 bit of representation of 14 bits, how many levels that can be produced using a 14 bit? Okay, so the number of levels is equal to L equal to 2 power of n number of bit. Okay, so 2 power of 14, we can get 16,384. Okay, so they're gonna be 16,384 levels, all of it. Okay, and then what? The number of voltage increment B, question B, the number of voltage increment used to divide the voltage range. So how many step size? How many step size used in the quantization? So this is actually, question B is actually referring to the dynamic range. So dynamic range actually will be learned after this. This one. Okay. So dynamic range is the number of quantized level excluding 0 volt. Okay, is the number of level excluding 0 volt. So that means this is equal to 2 power of n minus 1. Okay, so these are the number of voltage increment. How many step size? Berapa banyak anak tangga? Okay, and the number of increment or the number of step size is excluding 0 volt. So that's why we minus 1. We do the minus 1. Okay, and then what? C, question C, find the resolution of the digitization expressed as the smallest voltage increment. Now, find the resolution. So how to find the resolution? So resolution, okay, resolution is actually equal to range of voltage, voltage range, okay, from maximum to minimum, divide with the dynamic range, 2 power of n minus 1. Okay, so we get the voltage range, we divide with the number of step size excluding the 0 volt. Okay, so the total voltage range divide with the number of increment, divide with the number of step size. So daripada total voltage itu kita bahagikan dengan jumlah anak tangga, jumlah step size, jumlah step. Okay, tidak termasuk 0 volt. Okay, so from here we get here is 12 divide with the dynamic range that we get 16,383. Okay, so you will get 0.7325 millivolt. Very small. Okay, very small. Okay, so from, if you draw the here, if you draw the graph, okay, from 6 until -6, okay, so there gonna be a lot of levels over here, 16,383 levels excluding the x-axis. Okay, so if you want to find the next level after -6, okay, so after -6 volt, okay, this is volt, this is okay, so after -6, the next level would be -6 plus with a step size 0.7325 millivolt. Okay, so the next level would be, so you can use your calculator, try use your calculator, -6 plus 0.7325 milli. So the next level would be -5.9999999 2675 volt. Okay, this is the next level. After -6 would be this one. Similar with the above part, the next level after 6 volt would be 6 minus 0.7325 millivolt. So it would be how much? So 6 minus 0.7325 millivolt. So this is 5.9992675 volt, and so on. Okay, so if you want to find the voltage, you need to do one by one. Okay, so in the exam normally we are not asking up to 100 of bit, okay, like this. But if you want to find out, actually you can detect this is according to the number of bit, because this is 14, so it is at which line actually, okay, at which line. So if you can get, for example, it is the 10 line after -6, for example, if it is a 10 line after the -6, for example, you can just make it as 10 multiplied with the resolution. Okay, so you get the distance, and then you can plus with the minimum, -6 plus this one. For example, this is just example. If I know that the location is 10 level below the minimum, 10 level above the minimum, So 10 multiplied with the resolution, so we get the distance, and we can identify the location by doing the manual calculation, minus 6 plus, for example, 10 minus multiply with resolution. So we can get how much is the value of that quantized level. Okay. So if you have question about this, you can ask. Okay. So if you don't have question, I will move to the next slide. Okay, kalau ada soalan boleh tanya, no problem. Okay. SQR, signal voltage to quantization noise voltage. So signal voltage divide with the quantization noise voltage, which is SQR equal to V. V is the signal voltage divide with the quantization noise voltage. Qn, we already seen this one in the previous slide, quantization error or quantization noise. Okay, so the SQR minimum would be occurs for the lowest magnitude of quantization voltage, which is the V min divide with Qn. And for the SQR max occurs for the maximum quantization voltage, Vmax divide with Qn. Okay, so SQR don't have the unit. It is a unitless parameter because it is a voltage divide with voltage. Okay. Dynamic range. So dynamic range is the ratio of largest possible quantized voltage to the smallest possible quantized voltage other than the 0 volt that can be decoded by the digital to analog. Okay, this is DAC. Okay, so DAC is normally in the receiver side where we want to convert digital into analog. Okay, if you want to convert digital to analog, we use a DAC, or the short form is a DAC. If you want to convert analog to digital, we using the short form is a ADC. Okay, just a short form. So DR, dynamic range, is a Vmax over Vmin. So the Vmax here is actually the maximum quantized voltage that can be discerned by the DAC in the receiver. Okay, and the resolution is the step size. Or you can say that the dynamic range is equal to 2 power of n minus 1. The number of levels minus the 0 volt. Okay, that is a dynamic range. And dynamic range can be expressed in terms of decibel, which is 20 log of dynamic range. So we get in decibel. Okay. So example 6.5. So this is also a good example. So this example has come out in the previous final exam. We have asked this question, the same question in the final exam. So this is before the COVID pandemic. We have asked this question. So the question is similar. Maybe the value is different maybe. Okay. So the question is something like this. Okay. So example 6.5 for a PCM system with the following parameter. Maximum analog input frequency. Okay, so this is actually referring to the maximum input frequency, in maximum message frequency, and the maximum decoded voltage at the receiver would be, okay, would be this one plus minus 2.55 volt. So that means the quantization, the range is from 2.55 until minus 2.55. Okay, so these are the quantization levels of voltage. Okay, so they're gonna be a few range. There are gonna be a few levels of quantizations. And the minimum dynamic range, okay, minimum DR would be 46 decibel. And then what? Find the minimum sampling rate. Sampling rate, the minimum would be equal to, according to Nyquist said that the minimum rate for sampling would be 2 times the highest input frequency. So it is equal to 2 times 4. So this is 8 kilohertz. Okay. And then what? The minimum number of bit used in the PCM code. This one. Okay. So the answer is already here. Okay. So for question B, determine the minimum number of bits used. You want to know how much is the value of n, the minimum number of n that can be used in this example. So number of n, we can find the number of n, the number of bit based on the dynamic range. Okay, so the dynamic range is given as 46 decibel. 46. That's the minimum dynamic range. And dynamic range in decibel, it is actually 20 log DR. Okay, so 20 log. So 20 log DR is 46 dB. Okay, so 20 log DR is equal to 46. Okay, so how much is DR? So you see that 46 divide with 20. Okay, and then antilog of 2.3, antilog of answer, you're gonna get 199.5. Okay, so DR, after we do the antilog, we can find this as 199.5. 199.52623. So in this example, just use 0.5. Okay, and 199.5 is actually equal to 2 power of n minus 1. Okay, so 2 power of n is equal to 200.5, which is this one. Okay, and then we can find n by doing a log on both sides. Okay, log. So 2 power of n is equal to 199.5 plus 1. Okay, so if you want to find, so this is actually 200.5. So n is equal to log 200.5 divide with log 2. Okay, so you will get 7.63. 7.63 is the minimum bit, but there's no point number, there's no decimal point of number of bit. Okay, it is either 7, 8, 9, 10, or it must be an absolute value. It cannot be in decimal point. Okay, so if n is equal to 7.63, we cannot say that the minimum is 6. We cannot say that the minimum number of bit is 7. Otherwise, we will neglect the 0.63. So that's why the minimum number of bit that we must use will be 8. Okay, we cannot use 7, otherwise we will neglect the 0.63. So the best way would be to choose a little bit higher, which is 8. Okay, so n is equal to 8 bit. So we must use 8 bit for the for this process, for the quantization process. Okay. So if we use 8-bit, that means the dynamic range would be a little bit higher compared to the given minimum dynamic range. So it is given in the question that the minimum dynamic range is 46 dB. So this is if we use 7.63 bit. Okay, 7.63 bit. But if we use 8-bit, that means the dynamic range or the actual dynamic range would be a little bit higher. Okay, so how much is the actual dynamic range? It would be 20 log 2 power of n minus 1. So n becomes 8. Okay, if you use n equal to 8, that means 20 log 2 power of 8. 2 power of 8 would be equal to 256. And then minus 1. So we get 48.3 decibel. So this is the actual dynamic range if we use a 8-bit. Okay, so now we're going to use a 8-bit. Okay, we're going to use 8-bit. We cannot use 7.63. Okay, and then what? Question C. Okay, the next question asks you to find the resolution. Okay, so resolution is equal to the range of voltage from maximum to minimum, which is V peak to peak, divide with the dynamic range. Okay, so that means the range of voltage peak to peak 2.55 positive until minus 2.55. So 2.55 minus negative 2.55, so you will get 2.55 plus 2.55. Okay, so it is actually like this, 2.55 minus negative 2.55. So that's why you get plus. Okay, divide with 2 power of 8 minus 1. So this is, we're gonna use the minimum number of bit, which is 8. We cannot use 7.63. Okay, so 7.63 is from the given minimum dynamic range. So that means the dynamic range must be more than 46. Okay, so 2 power of 8 minus 1, so you're gonna get the resolution equal to 0.02 volt. Okay, this is the resolution. This is the step size, the distance between each quantized level. Okay, and then what? Find the quantization error. So this is actually referring to the maximum quantization error, which is resolution divide with 2. Okay, so the maximum quantization error is resolution divide with 2. So 0.02 divide with 2, so we're gonna get 0.01 volt. So this is the maximum quantization error, or maximum QN. Okay, or maximum QN. Okay, so do you have question to ask about this example? You can ask now before we move to the next slide. Okay, boleh tanya kalau ada yang tak faham, boleh tanya. I will try to explain again so that you understand about this. Okay. So no question. So I hope that you understand this. Okay, so I will move to the next example. Okay, I'll move to the next example. Boleh? Saya pergi kepada next slide. So before I proceed, can I get your response? Are you still there? Students, can you hear my voice?
Yes, Doctor.
Okay, thank
Boleh,
you.
Doctor.
Okay, thank you for the response. Kalau ada soalan boleh tanya, jangan segan-segan. Okay, you can ask me always anytime. Okay, so if there's no question, we're gonna see about the two types of quantization, which is uniform quantization and also the non-uniform quantization. Previously, you have seen the uniform quantization where each levels are the same. There's also non-uniform quantization where the step size are different. Okay, and if you see from here, for uniform quantizations, in uniform quantization, uniform size in quantization level, quantizing speech signal result in some of the quantization steps to be wasted. So if we sample all types of signal equally, there gonna be some problems where we're gonna wasted some of the some of the step size for certain signals, certain type of signals. Okay, so quantization noise is the same for all signal magnitudes. Okay, so if we assume that quantization noise same for all magnitudes, this is gonna produce a worse SQR, signal to quantization noise ratio. So SQR is worse of low level signal than high level signals. So what happened actually? So the issue is, if we assume that if we treat equally for all types of input signal, because the input signal has different kind of levels. Some of the input signal has a high amplitude, some of the input signal has a low amplitudes. So if we treat all the input equally, the error would be higher. Okay, for example, in this given picture, okay, in this given picture, you can see that a picture on the left shows the uniform quantization where each level or each step size are the same. Okay, and if you see from here, the uniform quantization is actually good for the strong signal, but if we see the weak signal, okay, weak signal, you're gonna see that we only have about 2 levels to quantize the weak signal. Compared to the strong signal, we're gonna have many levels. So if we have less level for the quantization, that means the accuracy would be lower, and that produce higher value of noise, especially for the weak signal. Okay, so what happened? If you see from the non-uniform quantization, you see that the step size are adaptive based on the input. Okay, so if the input is strong signal, we're gonna have the bigger step size. Okay, when it is a weak signal, you're gonna see that the step size becomes smaller. Okay, so we can quantize the weak signal more accurately. Okay, and if you see from here, even for the strong signal, okay, at the maximum steep, at the highest, in the steepest regions here, we can quantize, we can have many quantization levels in the steepest region over here, also for the strong signal. So we can have more levels to accommodate the variation of the input. Okay, we can have many levels, quantization levels, to accommodate the variation of the inputs. Okay, because the input is changing rapidly. Okay, so the quantizer must be suitable for the input. Okay, if the input varies strongly, so we can have bigger step size. Okay, and if the input is a weak signal, we can have a very small step size for the quantization. So this is adaptive to the input, which is better. We can reduce the quantization noise. Okay, so if you see from here, non-uniform quantizations, okay, provide fine quantization. Okay, fine quantization means small step size on low input signal, low amplitude input signal. and cross quantization, bigger step size for high amplitude of input signal. Okay, so how can we achieve the non-uniform quantization? How to do it? Okay, so in order to achieve the non-uniform quantization, okay, what we need to do is we need to distort the original signal with the logarithmic compression characteristic before applying to the uniform quantization. So what is this actually? We are distorting. Distorting means that we are modifying the input, okay, by going through the compression block diagram. Okay, if you see the block diagram, there's a one block diagram what we call as the compression. Okay, so compression means that we compress the signal, okay, based on a certain standard. Okay, and then we apply it through the quantizer. Okay, so compression, what's the purpose of compression? Compression allows small amplitude signal to become higher and high amplitude signal to become smaller. Okay, so this is almost similar with the emphasis and de-emphasis in the analog. In the digital, we have compression and compression and expansion. Okay, so compression, you assume that you compress the signal. Okay, so signal with a small amplitude value will become bigger, and high amplitude signal will become smaller. Okay, so and then we can pass it through the uniform quantization, quantizer. So that means we are actually modifying the input signal first, then we put it in the quantizer. Okay, so signal change at small magnitude will carry the uniform quantization through more steps than the same change at large magnitudes. Okay, so small magnitude signal will carry more many steps compared to the large magnitude of signal. So at the receiver, inverse compression or what we call expansion is applied so that the overall is not distorted. So if we compress the signal, that means we need to expand the signal with the same ratio in the receiver. Okay, so compression and expansion is similar with the emphasis and de-emphasis in the analog system. Okay, so compression and expansion, this is what we call as the compending process. Okay, so compending, there's two main laws, two main standards, which are the A law and also the mu law. A law is using in the Europe, mu law is used in the US and Japan standards. Okay, so if you see the this picture, okay, so that means small amplitude changes of signal will have more quantization levels, fine quantization, and high amplitude signal will have cross quantization levels, which are bigger step size. Okay, and you see that here, this is the picture to show about the compression, what happened during the compression. So this is the original signal, and you see that compress, you assume that you press the signal as if you're pressing the signal. So we are distorting the signal. We modify the signal amplitudes. Okay, we modify the signal amplitudes before we put it in the quantizer. Okay, so here we have the compressor. Okay, and then we put it in the encoder. Okay, and then we this is the medium, and then in the receiver we have the decoder, and then we have expander to expand again. Okay, so expand, assume that you pull the signal. Okay, assume that you pull the signal. Compress, assume that you press the signal. Okay, you press it like that, as if, okay, seperti seolah-olah kita press signal itu ataupun expander ni seolah-olah kita tarik dia punya signal itu seolah-olah dia punya analogy, the analogy is like that. Okay, and this is the compending characteristics for the A law and also for the mu law. Okay, so A law, if you see from here, A law is used in the Europe, mu law is used in the Japan, US and Japan. Okay, and we have asked this kind of we have asked this in the final exam previously. Okay, we have asked this in the previous final exam. And for this semester final exam, I suggest that you learn a lot about this. Okay, so this also important for this final exam, for this semester final exam. Okay, so what is this actually? Okay, so A law and mu law. Okay, so this govern how much is the output value. How much is the output value? Okay, how much is the output value? Okay, so compounding characteristic, there are two types of compression, what we call as a mu law, used in the North America and Japan. A law is used in the Europe. So for A law, okay, sorry, for the mu law is you see that y equal to so this is the output from the analog to digital converter. Okay, and this is y is the y max. We have a y max and y min. This is the levels of quantizer. Okay, the levels of quantizer. What is the level of quantizer? So we have seen previously, for example like this the levels. So where can I show you about this? Wait. Okay, so the levels of maximum levels for this, for example, the y max would be 3.5 y max. Okay, in terms of value it is a 3.5. Okay, and the input is depending how much is the minimum and maximum. Okay, if you ask me the minimum of the input signal, we should see the input from the before the sampling process. How much is the input values, amplitude? Okay, so let's go through this for a while. I pass through this. Okay, so y max is the maximum quantized levels, the maximum quantized level, multiplied with ln 1 plus mu. Mu is given from is based on the graph, based on the graph. So mu, either you can use mu 0 until mu 2.255. Okay, for example like this. Okay, mu multiplied with x is referring to the input. Okay, x is referring to the input. Okay, so x is the value. Okay, because x is depending on the range of input. Okay, so for example, your input signal is the range of magnitude is from, for example, 0 until 5 volt, for example. Okay, and your quantized level is from minus 10 until 10 volt. Okay, so the maximum y max, okay, is 10. Okay, in the form of values, and the maximum of x, the input in term of values is, in term of magnitude is 5. Okay, so you want to know how much is the output of the ADC, analog to digital converter, when the input is, for example, the input is 2 volt, for example. How much is the output? How much is the output? Okay, so maybe I can put like this. Let's do like this. Let's say a simple example. Let's I make it minus 5, for example. and let's say this is X, this is Y. Okay, so X is the input signal, Y is the level of quantizer. Okay, Y is the level of quantizer. Okay, so the value of X is varies from -5 until 5. Okay, so we want to know how much is the output of this compender, okay, using a mu law for input 2 volt. So how much is the output? Okay, remember compender means it will compress and expand the signal. So the output from this compender is Y max multiplied with ln in bracket 1 plus mu X modulus divide with maximum X. Okay, and then divide with ln 1 plus mu. Okay, so this SGN is a sign of X. Okay, so if the X value is more than 1, it is positive. If X is less than 1, it is negative. Okay, so this is the signage. SGN is the signage of X. Okay, the polarity of X, the polarity of the input. Okay, so this is for the mu law. Similar for the Y law, similar for the A law. Okay, similar for the A law. So maybe I can put line over here. Okay, similar for the A law. Okay, so before that, mu is the before that, mu and A is the mu and A parameter is the compression constant values. Maybe I should go through here. Maybe. So let's go through this graph so that maybe you can have a better understanding about these equations. Okay, so let's go through this. Okay. Okay, so you see that the input here is a compression characteristic for A mu law on the left and A law on the right. Okay, and this is the output of the compression compender given the input signal. Okay, and both input and output are in the form of what they call this input and output is represented in terms of the value divided with the maximum value. Okay, so it is from 0 until 1. Similar for the output, 0 until 1. Why is it like that? Because we divide the value with maximum value. Okay, so input is the input signal, output is the output from the compressor. Okay, and we have another parameter, as I mentioned earlier, is the range of what they call the quantizer levels. Okay, so let's go through here. You see that the value of mu is a constant parameter for the compending from 0 until 255. So if you see from here, if mu 0, the output will be linear. That means if you see from here, for input 0.2, you're going to produce output also 0.2. Okay, so it is looks like there's no compression at all. So the output is linear to the input. Okay, this is the output from the compender. Okay, and then what? For example, for 0.8, also 0.8 will produce 0.8. Okay, for mu equal to 0. So what about if we go to the maximum mu value, 255? Apa jadi kalau kita menggunakan mu yang lebih besar? Okay, so the higher the value of mu, the larger would be the compression characteristic. Okay, so here if you see mu 255, you see that for input 0, So for input 0.2, we will produce output around 0.7. Okay, with larger value of mu, we're going to produce bigger output with mu 255. For example, another example, if input is 0.8, okay, we're going to produce output here, for example, 0.95, for example. So you see that for larger input, the increment would be smaller. For smaller input, the increment would be bigger. Okay, so this is what happened when we do the compression process. Okay, similar with the A law. The higher the value of A, the higher the value of A, the larger would be the bigger would be the compression characteristic, compression factor. Okay, that means the higher the value of A, the signal will be more compressed. Okay, so if you see from here, we want to produce the output from the compressor given the input and also given the quantizer levels. Okay, so that's why we use these equations. Okay, so you see that okay, so you see that here for mu law, okay, y is the output of the y is the output of the quantizer. Okay, y is the output of the quantizer given the input. Okay, so here is the maximum level of quantizer. Okay, and here is given, here x is the input, the value that we want to find, how much the value of y given the value of x. Okay, so this is the input signal that we want to put inside the equations in order to find the value of y. Maximum, okay, maximum is the maximum input level, maximum input magnitude. Mu is the compression factor. SGN is the signage or the polarity of x, this polarity. Okay, so for example, if you are given input, for example, the range of input from -5 to 5, for example, and the range of quantizer is between the -10 to 10 volt, for example. So you want to know how much is the output of the quantizer if the input is 2 volt, for example. Okay, so you put inside 2 volt, and you know that the maximum would be 5 in terms of magnitudes, so you can get the ratio. Okay, x divided with the maximum, and you multiply it with the value of mu. It depends on how many mu you want to use. Okay, and then ln all of it. This is ln of 1 plus mu. Then you multiply it with, so this is actually like this. You multiply it with maximum quantized levels, which is 5, which is 10 in this example. Okay, which is 10 in this example. And signage of x for 2 volt, 2 volt is a positive, so that means this is just positive. Okay. Similar for the A law, for example, if you see from A law, we want to find the output of the quantizer given the input x and also the quantizer levels. Okay, so you see that here, so it is divided into 2 parts. Okay, depending on the ratio of x. over x max, the ratio of input. So if the ratio of input is more than 0 or if more than 0 or less than or equal than 1 over a, okay, that means you're gonna use this equation, the first equation, okay. So in order to find which equation we want to use actually, so you need to do the ratio of x over x max, okay. X is the input signal that we want to find the y value. X max is the maximum input, okay. So if the value less or equal than 1 over a, you need to use the first equation. The first equation say that output of the quantizer is equal to maximum quantized level multiplied with a multiplied with ratio of x over x max, ratio of inputs, divide with 1 plus ln a, multiply, and then the signage is depending on the input. If the input is negative, then the sign would be negative. If the input is positive, then the sign would be positive. So sign SGNX is just for the polarity, okay. And if the ratio of input x over x max is less than 1 or more than 1 over a, so we need to use the second equation. The second equation just a little bit different. 1 plus ln a multiplied with x over x max divide with 1 plus ln a, okay. So and then you need to multiply it with y max, the maximum quantized level, and the signage is depending on the x value. Okay. So there will be a question in the final exam. You need to find the output of the quantized level given the input and also the ratio of quantized levels, okay. So you will be given x min until x max, okay, and also y min until y max. You will be given the value of a as well, okay. So find the value of x. For example, x is in between this, find the value of x, find the value of y given the value of x. So for x volt of input, how much would be the output? It must be between this range, okay. So you need to find the output y in terms of volt based on this given equation, okay. So we have asked these kind of questions maybe once or two times in the previous semesters, okay. Previous semester we have asked about mu law, and for this semester we're gonna ask about A law. So I suggest you to do a lot of revision regarding the A law examples for this semester's final exam, okay. Remember, x is the input signal, analog input signal. Y is the range of quantized level, okay. So since this is involving the compression and compending process, so in order to determine the output, it is based on the A law or mu law, okay. For A law, there's a two equations over here. Which one you need to use? You need to find the ratio first. The ratio of x over x max, okay. Is it less than 1 over a? If yes, use the first equation. If the value is more than 1 over a, use the second equation, okay. So this is y max. The first equation is y max multiplied with A multiplied with ratio of x over x max divided with ln A. And the signage of the voltage, the polarity of the voltage, whether it is a positive or negative, is depending on the value of input. Okay? And for the second equations, y max multiplied with 1 plus ln A multiplied with ratio of x over x max divide with ln A plus 1. And the polarity is depending on the polarity of x. Okay? In the previous exam, we have asked the student to plot the output. Okay? We have asked the student to plot the output. In the previous exam, we give in term of table for the input. We give the table in term of input and also the y value. So find the output. So you need to plot and then you need to draw something like this. So for this semester, we will not ask you to draw. We will give you the value of A. We will give you the range of X. We will give you the range of Y. Then you need to find a specific output based on the specific input. So for certain value of X, how much is the output of the quantizer for A law, given A equal to something? Okay, so for you, I suggest you to find some examples or read some examples so that you understand about the A law. So A law will come out in the final exam. It is not difficult, okay? It is not difficult. You just need to use these simple equations to find the value of output of quantizer Y. Okay? So, this graph, okay? So, compression is actually like we signal that we compress it. Okay, so value of this input signal which is small will become bigger, and the high value of input will become a little bit smaller or small increment. Okay, so that's what the compression looks like, as if you compress it. Okay, so seolah-olah macam you compress the signal. Okay. So the higher the value of mu or the value of A, which is the compressor characteristic, the higher would be the increment for the small amplitude of signal. Okay, and for the high amplitude signal, there's gonna be a slightly increment for the A law and also the mu law. Okay, so untuk amplitude yang kecil akan mengalami perubahan yang besar dengan menggunakan faktor mu ataupun A yang lebih besar. Okay, kalau mu ataupun A besar, maknanya input signal yang kecil itu akan digandakan lebih banyak. Okay. Manakala untuk input mempunyai amplitude yang besar, gandaan itu menjadi kecil. So tujuannya, the purpose is that we want to increase the small input amplitude, and for the small amplitude we increase more. For the high amplitude, maybe we just increase it a little bit or just remain it the same. Okay, so we do the distorting. So this is what we call as the distorting the signal. We modify the signal, but when we modify the input signal, we cannot modify as what we like. It is based on the standard. So the distorting process, this is what we call as the compression and expansion or compending. Kita sebenarnya modify signal itu berdasarkan standard yang diberikan, A law and also the mu law. Okay. So if you want to ask question about this, you can ask, If I can find the example about this, I will show you later. If I don't have the time to show you the example, I suggest you to find many examples about A-law. Okay, because this will come out in this semester's final exam. Just to calculate the output given the input. Okay, and you need to know this equation. Please make sure that you know how to use this equation. Okay, in these lecture notes, there's no specific example. Okay, there's no specific example. Okay, but remember, in the final exam, we will give you the range of X, the range of Y. So you need to find how much is the output based on the specific input. Okay. Okay, the third process is encoding. The third process is encoding. So encoding is the process of, okay, this is the third process. I remember the first process is sampling. The first process is sampling. The second process is quantization. The third process is encoding. Okay, remember the first is sampling, second is quantization, third is encoding. So encoding is the process of assigning a specific code word to each of the quantized levels. Okay, we are assigning specific code to each of the quantized level. So this is what we, the output of this encoding process is what we call as the PCM, pulse code modulation. Okay, so the output of encoding is what we call as PCM. Okay, so for the baseband transmission, the code word base will then be transformed into pulse waveform. So if you want to transmit as a baseband transmission, we need to change the PCM into a waveform, pulse waveform. That means because this PCM is in the form of logic 10 10 10 10. Okay, PCM is a code word. PCM is a code word. So if you want to transmit this signal baseband using a line, using a wired transmission, wired medium, you need to change this into electrical pulses. Okay, that one is after you produce the PCM code, then you need to change it into pulses. That one you can use a line coding, which you will see later. Okay, so the choice of voltage level is guided by two constraints. The quantized interval between levels should be equal, inconvenient for level. Okay, quantization produce. Okay, so we're gonna see this about this encoding process. So encoding process, I skip to this part. I skip one slide to this part. So we have seen this in figure 6 previously. So now we want to see the last two lines over here. Okay, because we have seen this example previously. So if you see from here, okay, from here, we have 8 levels. Okay, this is from the previous examples. We have 8 levels from minus 3.5 until 3.5. Okay, and since we have 8 levels, that means actually we are using 3-bit, okay, to produce 8 levels of quantizations. Okay, so 8 level of quantization, that means from 0 until 7, 0, 1, 2, 3, 4, until 5, 6, 7. Okay, so we have 8 levels. So 8 levels, okay, the way we assign the code number, we assign the smallest code number to the smallest, to the lowest levels of quantizations, which is minus 3.5. Okay, we are not starting from 7, we are starting from below. Normally like that, and that's the practice of the standard practice. 0, and then the next quantization level 1, code number 1, code number 2, 3, 4, 5, 6, 7. So total will be 8 levels. So what is this code number? This code number is actually in binary. It is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So the decimal code number is also represented by the binary code number. Okay. So if you see from here, the first sample is 1.3. We quantize to the nearest quantized level 1.5. So 1.5 volt, this one, is represented by code number 5. So code number 5 is 101. Okay. And then what? The next sample I show you. The next sample is 3.6. And then we quantize to the nearest level is 3.5 volt. So 3.5 volt of quantization level is assigned with code number 7. Code number 7 would be 111. 111. Yeah? 111. Okay. And then the next sample value is 2.3. Okay, we quantize to the nearest level, which is 2.5. Okay, so the nearest level is 2.5. So 2.5 is assigned with the code word number 6. So code word number 6 in binary is 110. Okay, and so on, dan seterusnya. So encoding, we assign the quantized level to the nearest. We assign a code word to each of the quantized level. So that is the encoding process. Okay. So if you see from here, okay, if you see from this picture, from this example, we're gonna have we have 1, 2, 3, 4, 5, 6, 7 samples. Okay, and the output of this, after encoding, we are producing all of this sequence of codes. Okay, we are producing these codes 101, 111, 110, 100, 01, 011, 001, and also 000. Okay, so these are the PCM code word. Okay, PCM code word. Okay, and each of these is what we call as a symbol. Okay, symbol. One symbol contains 3 bit because we are using 3 bit. One symbol contains 3 bit. Okay, in this example. Okay, so we have 1, 2, 3, 4, 5, 6, 7. 7 multiplied with 3, so we have 21 bit of output for this example. Okay, 21 bit of output for this example. And if you see from here, so this is an example of PCM encoded signal in binary form. Okay, so you see that from this example, for the first sample is quantized to the number 5. So 5 is 101. So you see that this is from 000 until 111. So 101, the first sample, number 5. Second sample, number 7, 111. Third sample is 6 at 6 volt. Okay, 6 is defined as sorry, not 6 volt. This is Okay, so this is 6 volt is representing with 110. Okay, and so on. The last one would be another 5 volt. 5 volt is representing as 101. Okay, so we have 10 samples over here, so which is 33 bit of output. Okay, so this is the output of the PCM encoder. The output of the encoder. Okay, and similar for this picture on the right and picture on the left below. Okay, this is compressions by reducing the number of quantized level. So there are many types, there are many methods of compression process. First, we can compress by reducing the number of quantized level, or we can compress by reducing the sample frequency. So this is methods for the compressions. Okay, so in this slide, it is shown what is the difference if we compress by reducing the number of quantized level. Okay, that means we compress the signal by reducing the amplitudes. Okay, or we compress by reducing the number of sample that we take. Okay, so there are actually many methods for the compression. In this example, it shows 2: compression by reducing the number of levels. So this is the picture on the left below, and compression by reducing the number of sampling frequency on the right. Okay, so these are the methods of compression. Okay, ada pelbagai kaedah compressions. So let's look at the example 6.6. For a PCM, the bit for PCM, the bit PCM code, the folded binary code, determine the quantized voltage, quantizations error QE, and also the PCM code for the analog sample voltage of 1.07. Okay, folded binary is 1.07. So folded binary is this one, and if you see the folded binary, how much is the value? 1.07. So 1.07 of input, 1.07 is over here. Okay, it will be rounded up to the nearest quantized level, which is 1 volt. Okay, which is 1 volt. Okay, so the quantization error, if we round it up from 1.07 to 1, that means the error, the rounded up value would be 1 modulus 1 minus 1.07. Okay, which is equal to 0.07. Okay, so sample value 1. Okay, so okay, previously it's like this. Previously in your notes it is a sample value minus quantized level, so 1.07 minus 1. Okay, so we get 0.07. And this one, quantized level number 1, quantized level 1 is actually representing by code number. Okay, by code number 101. Okay, code number 101. Okay, so quantized level 1 volt is represented by code number 101. Okay, so this is the folded binary PCM, which is based on this example. Okay, Any question you can ask. If you want to ask question regarding this, please ask question. Otherwise, I will move to the next slide. Okay, otherwise I will move to the next slide. Okay, so if you have question, please ask. Otherwise, I will move to this slide. Okay, this is about PCM transceiver block diagram. So transceiver is transmitter and receiver. Okay, so we have the analog input. Okay, we use the band pass filter to filter the desired frequency and remove the unwanted frequencies. Okay, and then we do the sampling process, sample and hold, to produce a pulse amplitude modulation signal. Okay, and then we put inside the analog to digital converter, this is a ADC, to do the process of quantization and also to do the process of encoding. Okay, and then after we produce a PCM code, we need to convert it into electrical pulses. Okay, which is done by the parallel to serial converter to produce a output in terms of electrical pulses, and then we transmit into the medium to the receiver. So since the distance, okay, since the distance is, so since the distance between transmitter and receiver is very far, okay, so what happened is that we can use a few repeater to regenerate the signal. Okay, so that we can transmit in a longer distance. Okay, and then serial converter to convert the electrical pulses into a PCM code word, and then digital to analog to convert into palm signal. Okay, and then we can put inside the whole circuit to produce the output signal, and then we can use low pass filter to select the low frequency signal, and we're gonna get the output as analog again. Okay, PCM system with analog compending. So the difference is that we have the analog compressor and also analog expander at the receiver. Okay, so for this we have the analog input, we have the band, and then put inside the band pass filter to select the desired frequency band, and then we put inside the compressor, okay, to compress the signal according to the A law or mu law. Okay, and then put inside the sample and hold circuit for the sampling process to produce palm signal, and then we put inside the ADC to do the quantization and encoding process, and then we put inside the parallel to serial converter to change it from PCM code word into electrical pulses. Then we transmit across the medium, then arrive at the receiver, and then serial to parallel converter to convert the electrical pulses to PCM code word, and then we produce, we put inside digital to analog to convert into analog to produce palm signal, and then whole circuit, and then here we put inside the analog expander to expand again with the same factor as we do with the compressor previously. And then we have the band pass filter to select only the desired frequency band. Then we produce the analog output. Okay. Okay, this is also the important parameters. The important parameters for the digital modulation. Okay, so there are three important parameters here, which is signaling rate, bit rate, and also the bandwidth. Okay, so signaling rate SR is equal to 2 times the highest signal frequency FM. So this is actually the sampling frequency. Okay, sampling rate is actually the fs. Okay, how many samples that you take per second. Okay, so this is based on the Nyquist theorem as well. Okay, and you produce the output of sample in terms of sample per second or in terms of hertz. Okay, and then the second parameter is the bit rate. So bit rate is defined as the speed of transmission. Bit rate ini adalah menggambarkan kelajuan penghantaran. Okay, bit rate is the speed of transmission, is equal to the sampling rate multiplied with the number of bit per sample. Okay, so this is sampling rate is the sample per second, you multiplied with the number of bit. Okay, you multiplied with the number of bit per sample. Okay, so what happened is that you will produce the output in terms of bit per second or BPS. Okay, this is to show the speed of transmission. What about the bandwidth? So the bandwidth of binary PCM depends on the bandwidth of PCM waveform depend on the bit rate and the waveform pulse shape, sync X or rectangular pulses used to present the data. Okay, so this pulse shape is the pulse that we use during the sampling process. Either it is a sync function or rectangular function. Okay, and the bandwidth here consists of two types of bandwidth that we can calculate actually. The first one, if we use a sync function, okay, to generate the PCM waveform. So that means we use a sync function of pulse during the sampling process. Remember the sampling process, we multiply the input with the with another signal, with a pulse signal. So if the pulse is in the form of sync function, that means we're going to produce bandwidth equal to half of the bit rate. Okay, so the minimum bandwidth would be half of the bit rate. What is this actually? So if the bit rate is equal to for example if the bit rate is 1 megabit, that means the bandwidth would be, the minimum bandwidth would be half of the bit rate, which is 500 kilo, but the unit is in terms of hertz, half of it, half in terms of magnitudes. Okay, so this is if we use a sync function for the sampling process. Okay, and if we use a rectangular pulse, that means the bandwidth that we produce is equal to the bit rate in terms of magnitude. Okay, so that means if the bit rate is 1 megabit per second, the bandwidth produced from this process would be equal in terms of magnitudes which is 1 mega, but in terms of bit per second. In terms of, 1 megahertz. So bandwidth is in terms of hertz. Okay, bandwidth in terms of hertz. So this is if we use a rectangular pulse shape during the sampling process. Okay, so normally in the practical case we are using this one. The bandwidth for the PCM using a rectangular pulse is equal to the bit rate. Okay, normally we use this. So this is also known as the bandwidth of the PCM. While the above here is what we call, this is also known as the minimum bandwidth for the PCM. So normally when we ask how much is the bandwidth, so we are actually referring to this one actually. Okay, but if the question asks how much is the minimum bandwidth, it is actually half of the bit rate. Okay, so these parameters have been asked in the previous final exams many times. Banyak kali pernah ditanya. Okay, for example, if you see from here, an analog signal with a frequency of 40 kilohertz is sampled at sampling frequency equal to the minimum Nyquist sampling frequency. Each sample is encoded using 4-bit PCM. Determine the bit rate. So you are given input frequency FM is 40 kilohertz, sampling equal to the minimum Nyquist rate, which is 2 FM. So the sampling rate is equal to 2 times FM, which is 2 times 40 kilohertz. So we produce 80 kilohertz. Okay, and how much is the bit rate? So bit rate is equal to number of bit multiplied with the sampling rate. So number of bit per sample multiplied with sampling rate, so we get 320. The unit is kilobit per second. Okay, so this is the number of bit. Okay, so if you have question, please ask. Otherwise, I move to the next example. Okay, this one. Determine the bit rate of a pulse code modulation PCM transmission is fixed at 63 kilobit per second. Calculate the bandwidth. Okay, so in this example, the question asks how much is the bandwidth of PCM. The question doesn't mention about sinc function or rectangular pulse train. So this is just bandwidth of PCM. So that's why, as I mentioned earlier, normally when we ask how much is the bandwidth of PCM, the bandwidth of PCM is equal to the magnitude of bit rate. Okay, so if the bit rate is 63 kilo, that means bandwidth would be 63 kilohertz. Okay, and then what? Analog signal with frequency 4 kilohertz is sampled at sampling frequency 10% higher than the minimum Nyquist sampling frequency. That means 10% above minimum, 10% above 2 FM. Okay, 10% higher than 2 FM. So each sample is encoded with 3 bit n equal to 3 before transmitted into the channel. Determine the bit rate. So for your information, we have asked this kind of question in the previous final exam. Okay, we have asked this in the previous final exam. Okay, we have asked this kind of question previously. Okay, where we sample a few percent higher than the minimum sampling frequency. Okay, so the first one, bit rate. Determine the bit rate. So how to determine the bit rate? BR. Okay, so bit rate, in order to find the bit rate, first we need to find the sampling rate. Okay, so sampling rate, if you see from here, the minimum sampling rate according to the Nyquist, it is 2 FM, 2 times the input frequency, which is 4 kilohertz. Okay, that means 2 times 4, so we get it as 8 kilohertz. Okay, 8 kilohertz. So this is the minimum sampling rate. So the actual sampling rate is given in the question that 10% higher. That means the actual sampling rate is sampling rate plus 10% higher. Fs, sampling rate, sampling frequency, plus 10% of sampling frequency, because it is a 10% higher. 10% from the minimum. Sorry, 10% more than the minimum. So that means the minimum sampling frequency plus 10% of the minimum. Okay, so that means the sampling frequency would be 8 kilo, okay, the minimum sampling rate, plus 10%. So that means we are sampling at 8.8 kilohertz. Okay, so you see the difference here. When it is said that 10% higher, that means minimum plus another 10%. Okay, 10% higher than the minimum. Okay, so normally students do careless mistakes over here. Okay, normally students did careless mistake over here. Okay, so it is 10% higher. That means you need to plus with the 10% plus minimum, because it is 10% above the minimum. Okay, then the bit rate is equal to the number of bit used, 3 bit, multiplied with the sampling rate. So we get 26.4 kilobit per second. Okay, so 3 multiplied 8.8 kilo, so you're gonna get 26.4 kilobit per second. Okay, and then the next question asks the bandwidth of the Pcm waveform. So this question does not mention whether this is a sinc function, using a sinc function, or using a rectangular pulse train. Okay, so when we mention about bandwidth Pcm, normally most of the time the bandwidth of Pcm is equal to the bit rate. Okay, so bandwidth of Pcm equal to the bit rate in terms of magnitude, okay, which is 26.4 kilo, but the unit is in terms of hertz. Okay, same, the magnitude is the same, but the unit is different. Remember, the unit for bandwidth is in terms of hertz. Okay, so do you have question about this? If you have question, you can ask me. Otherwise, we can move to the next slide. Okay, otherwise we can move to the next slide. Kalau ada soalan boleh tanya. So can I get your response? Are you still there? Can you hear my voice? Can I
Boleh,
get...
Doktor.
Okay, thank you for the response. Again, I'm afraid that I'm talking to myself. Okay, saya risau saya cakap seorang-seorang. So maybe we can take a break for how many minutes? Maybe 5 minutes until 4:10. Okay, we're gonna take around 7 minutes. Okay, until 4:10. You can have a glass, or maybe I want to make a coffee. So that we will continue again at 4:10. Okay, 4:10 p.m. I will continue again. So feel free to go anywhere you like. I will start again at 4:10 p.m. Okay, 4:10 minit saya akan sambung. Okay, let's take a break for a while. Okay, so we continue again at 4:10 p.m. Okay. Okay, shall I continue again? Can I get your response? Are you still there, students?
Yes, Dr. Ken.
Okay, thank you for the response. Okay, so we have take a break for a few minutes, and now we will continue again for the next slide, which is about baseband transmission. Okay, so baseband transmission is known as the low frequency transmission, where we only use the same frequency as the input frequency. We are not converting the input frequency from low frequency into higher frequency. And normally for the baseband transmission, we transmit the signal in the wired medium. Okay, normally we transmit baseband transmission inside the wired medium. Okay, and if you remember, up to the previous slide, we have learned about the formatting process. Okay, we have learned about sampling, formatting, and also the encoding. Okay, and we produce the Pcm code word. So Pcm code word is in the form of logic 10101010. Remember, 1010 is not a number, it is a logic number. Okay, so when we produce a code word, logic is a Pcm code word, logic 1010. Now the issue is, how are we going to transmit this code word into the medium? Macam mana kita nak hantar medium ini ke dalam macam mana kita nak hantar code word ini ke dalam medium. Okay, that's the issue. Okay, so we have two options. Whether we want to transmit the code word in the form of baseband transmission, or we want to transmit the code word as a bandpass transmission. Okay, so baseband transmission does not involve modulation with the analog carrier. So baseband transmission ini tidak melibatkan modulation dengan analog carrier. Normally for the baseband transmission, we are using the same frequency as the input for transmission, and normally we transmit along the wired medium. Different from the bandpass transmission, or what we call as a digital radio transmission, where we do the process of modulation with analog carrier, which you will see later. Okay, so now we want to use a baseband transmission. That means we want to convert the PCM code word into electrical pulses. So the way we can do that is by using a line coding. So we are actually want to use a pulse converter that convert the code word into electrical pulses. So we want to make it in terms of voltage, voltage variation. Okay, for logic 1, how much is the logic 0, how much is the voltage. Okay, so in order to do that, we can use a line coding. Okay, so there are two types of what we call as the there are two types of line coding, whether it is written to 0 or non-written to 0. Okay, and there's the main types are whether it is written to 0 or non-written to 0 volt. Okay, and under these categories, there are many types, there are many methods of line coding. Okay, so we have the non-written to 0, and also we have the phase encoded, we have a written to 0, and also multi-level binary. Okay, there are many others actually, not only 4, there are many more. Okay, so now the issue is we want to convert this PCM code word into electrical pulses. So either we want to make it written by a unipolar or bipolar. Okay, so we can represent the output as a unipolar or bipolar. So unipolar means that it is one single polarity only. Okay, single polarity. Bipolar means it has two polarity of output, positive and negative voltage. Okay, so it depends on the applications. Okay, it depends on the applications which one we want to use. And if you see in most practical applications, normally we use a bipolar output, which has a two polarity of output, positive and negative. Okay, so these are the examples. So there are many types of line coding. Okay, so let's look on the left side. Okay, the left side. Okay, I want to show you about the left side of line coding. You are given the input. Okay, you are given the input PCM code word. Okay, now the input is digital. Okay, remember we have the digital input. We want to produce the pulses. Now the input is digital code word. We want to produce pulses, electrical pulses. Because we cannot transmit 1010, we need to transmit in the form of electrical pulses, which has the voltage variation. Okay, So the first one is you see that the input is 1011000101. Okay, so if you want to use a non-written to zero L, L means level. Okay, L means level. So N non-written to 0 means that it is not written to 0 volt. Okay, non-written to 0, that means the output will not return to 0 volt. Okay, so for this non-written to 0 L, L is level. So so for non-written to 0, you see that the changes, okay, so changes happens when the input change from 1 to 0 or 0 to 1. Okay, the output will change only if the input codeword change from 1 to 0 or 0 to 1. And if the input is the same value, no change. So let's do this. You see that the first one is 1, input logic 1, produce positive output voltage, and then the next is input logic 0, it will change to negative polarity at the output. Then the output change again to input logic 1, so the output will change from negative to positive. Then the next input is logic 1, so no change. Then the input changed logic to logic 0, so the output will change into negative voltage. And then no change in the input, still logic 0, so no change in the output. Again, no change. Then the input changed to logic 1, so the output will be positive voltage, and then no change, and then negative voltage, and then positive voltage. Okay, so NRZL change whenever there's a conversion to the from 1 to 0 or 0 to 1. Okay, what about NRZM? What about NRZM? Okay, so NRZL, okay, so NRZM, M is a mark. Okay, NRZ, M is a mark. If you see the M here for mark. Okay, so NRZM change whenever there's an input logic 1. So whenever there's an input logic 1, the output polarity will change. Okay, for example, so the first one is input logic 1, then the next is input logic 0, so no change. Remember, changes only happen when the input is logic 1. Then the third input is logic 1, so you see that the output will change polarity from positive to negative. Then the input is another logic 1, then the output polarity will change from negative to positive output voltage. Then the input logic is 0, so no change, another 0, no change, another 0, no change. Then the input logic is 1, so change polarity from positive to negative, another one, change polarity to positive, 0, no change, and then 1 change to negative. This is non-written to 0 mark. And for non-written to 0 S, S means space. So S is inversion of M actually. So NRZM means that changes happens when the input is logic 0. Okay, so for example here, starting here, so students might ask me normally for the first bit, what should I do? Okay, what should I do for the first bit? Should I put positive here or should I put negative? Okay, so the first bit is doesn't matter. Okay, you can start with the positive or you can start with the negative. Doesn't matter about that. Okay, in this example, it starts with negative for the input logic 1. Okay, and remember for NRZS, every input logic 0 will change the polarity. So from negative to positive. Input logic 1, no change. Another logic 1, no change. And then input logic 0, change polarity from positive to negative. Okay, from positive to negative. Then another input 0, change polarity to positive. Another input 0, change polarity from positive to negative. And then input logic 1, no change. Input logic 1, again, no change. Then input logic 0, change polarity to positive. Input logic 1, no change. Okay, so that one is NRZ space S. Okay. Then if you see another one is a unipolar. Unipolar means a single polarity. Normally the positive voltage. Okay. Unipolar return to 0. So it will always return to 0. Okay. It will always return to 0 for every bit time. Okay. Half of the bit time will return to 0 volt. For example, so for unipolar RZ, input logic 1, okay, input logic 1 will change to positive voltage and then return to 0 again. For input logic 0, no change, will be at 0 volt. Okay, so you see that input logic 1, it will become positive output voltage and then return to 0, another half bit time. Input logic 0, no change, will be at 0 volt, stay at 0. Input logic 1, become positive output voltage, return to 0. Another one, positive output, return to 0. And then 0, 0, 0. So it will stay at 0 volt. And then here 1, input 1. So logic positive voltage, return to 0. Positive voltage, return to 0. And then no change for input logic 0. And then input logic 1, positive voltage, output, and then return to 0. So this is return to 0 unipolar. Okay. Then we also have a return to 0 bipolar. Okay. So bipolar, we have two polarity of output, positive voltage and also the negative voltage. But this one, it will always it will also return to 0 for both input logic 1 and also input logic 0. Okay, if you see from here, input logic 1, it will produce positive voltage, half bit time, and then return to 0. And then input logic 0, it will produce negative output voltage and then return to 0. Input logic 1, positive output voltage, return to 0. Another input logic 1, positive output voltage, return to 0. And then 0, 0, 0 input, it will be negative voltage, return to 0. Negative voltage, return to 0. Negative voltage, return to 0. And then input logic 1, positive, return to 0. Positive, return to 0. And then input logic 0, negative output voltage, return to 0. Positive, and then return to 0. Okay, so this is bipolar, return to 0. Okay, and we also have here return to 0 alternate mark inversion. So for alternate mark inversion, it will change polarity for half of the bit time every time the input is logic 1. Okay, so setiap kali ada logic 1, dia akan bertukar polarity. Otherwise, it will stay at 0 volt. Okay, so for example, here is input logic 1, start with positive output voltage, return to 0. And then input logic 1, no change. Input logic 0, no change. Then input logic 1. Remember, every input logic 1, it will change polarity from the previous. So this has memory of the previous. That means if the previous is positive, now input logic 1 will produce negative output and return to 0. And then another input logic 1 change polarity from negative to positive, return to 0. And then input logic 0, 0, 0, 0, so no change, remain at 0 volt. Then input logic 1, so previously is positive, now becomes negative output voltage, return to 0. Another input logic 1, positive, 0. Input logic 0, no change. Then input logic 1, change polarity, previously is 1 volt. Okay, we see the previous input logic 1 is positive, and then it will become negative. Okay, so I think on the line coding on the left is enough for you to study, and you can learn by yourself for the Pcm waveform on the right side. So there are many types of line coding. Okay, so for you is enough until RZ AMI. Okay, for you to understand about this. The way we change the code word into electrical pulses. Okay. So I have explained about this. So these are the explanations. You can read on your own the explanations. Okay. Digital modulation. So digital modulation, or what we call as a bandpass transmission. So this is when we want to transmit the signal into the wireless medium. So when we want to transmit the signal into the wireless medium, that means we need to convert the signal into analog. Remember, now we have the input is digital. We already produced a digital PCM code word 101010. Now, if we want to transmit into the wireless medium, we need to modulate the digital input, the digital code word, with the analog carrier, so that we can produce electromagnetic waveform, which is a higher frequency in radio frequency, suitable for transmission. Okay, so in this case, it involves modulation, and we convert the low frequency into high frequency. Okay, so this process, we modulate with the analog carrier, which has a higher frequency compared to the input. Okay, and it's going to produce ASK, amplitude shift keying, or frequency shift keying, or phase shift keying. Okay, so if the modulation change the amplitude of the carrier in accordance with the input, we call it as the amplitude shift keying. If the modulation change the frequency of the carrier in accordance with the input, it will produce FSK, frequency shift keying. If the phase of the carrier change in accordance with the input variation, then we call it as phase shift keying. Okay, so ASK, FSK, and PSK are similar with the AM, FM, and PM in the analog. Okay, similar means setara. So similar does not mean same. Similar. Okay, it is not same, it is similar. Okay, because this process modulate with the analog carrier. Okay, and this is the block diagram for the digital modulations. If you see from here, this is the block diagram of transmitter and receiver. Okay, so we have the input data. Okay, so input data, we change it into digital code word, and then we put inside the modulator, we modulate with the analog carrier, and it will produce either ASK or FSK or PSK. Okay, and then we put inside the bandpass filter to filter out the unwanted frequency, and we amplify the signal and we transmit into the wireless medium. So within wireless medium we have the noise. It will disturb the signal, and then arrive at the receiver. We use a bandpass filter to select the desired frequency band, and then we amplify the signal, and then we do the demodulation process with the analog carrier to produce the output data. Okay. Energy bit over noise density, which is defined as EB over N0. EB is the energy bit, okay, average bit energy. N0 is the thermal noise power density. So this EB over N0 is an important parameter in the digital system, where it is similar or equivalent to the SNR in the analog. Okay, so EB over N0 ini adalah parameter penting yang setara dengan SNR in the analog. In the analog, we commonly use the SNR, but in the digital system, we normally use the EB over N0 as a performance parameter. Okay. So EB is equal to PR times TB. Okay, PR is the received power in watt multiplied with the bit duration in second. So you're going to get watt second or joule. Okay, and then N0 is the thermal noise power density, which is the Boltzmann constant multiplied with the noise temperature in Kelvin. Okay, so EB over N0 is a unitless parameter. Okay, EB over N0 is a unitless parameter. Okay, so both of this is in terms of joule and also joule. Okay, watt second and also watt second. Okay, capacity. Okay, so capacity is the maximum bit rate. Okay, channel capacity is defined as the maximum bit rate that can be decoded in the receiver. Okay, channel capacity is depending on the condition of the channel. Okay, which means that the transmitter must know how much is the channel capacity, so that it will not transmit more than the necessary bit rate. Okay, if the transmitter transmit more than the channel capacity, what happened? The receiver will be unable to decode the received signal into the original signal. Okay, kalau transmitter itu menghantar lebih besar daripada channel capacity, receiver tidak mampu untuk decode the received signal into original signal. Okay, so channel capacity also in terms of bit per second. Okay, the unit is bit per second. So channel capacity is defined as 2 times the bandwidth log 2 of M. Okay, M is the number of symbol. M is the number of symbol. Okay, M is equal to 2 power of n. Okay, M is equal to 2 power of n. Okay, here is using a K, so this is also referring to number of bit. Okay, therefore, if you see from here, minimum bandwidth necessary to pass the Emery digitally modulated carrier, which is the minimum Nyquist bandwidth in hertz, is equal to B over log 2 of M. B here is the bit rate. Okay, the B here is the bit rate. Okay, so the maximum B here is the channel capacity. If you want to find the maximum, it will be the channel capacity. Okay, divide with log 2 of m. So this is actually referring to the number of bit used in the system. Okay, so if you do log 2 of m, you're going to find the number of bit. Okay, and then so this is actually from here. Okay, so the maximum bandwidth would be C over K. Channel capacity divide with the number of bit. Okay, K is the number of bit encoded into each signaling element. Okay, so the bandwidth, okay, is equal to so why it is B over here. Okay, you can put any bit rate less than the channel capacity. The maximum would be the channel capacity. Okay, and then what? We have another term what we call as a baud. Baud is what we call as a symbol rate. Okay, baud is the symbol rate. So symbol rate, remember that we have bit rate and we also have symbol rate. Okay, symbol rate, the unit is baud, or you can say that in terms of symbol per second. So either you want to use baud or you want to use symbol per second. So how much is the maximum symbol rate? It is defined as the channel capacity divide with the number of bit. So you can find the maximum baud. Okay, so C is a bit per second, BPS. Okay, you divide with the number of bit per second. So you're gonna get symbol per second. Okay, so one symbol contains a few bits. Okay, one symbol contains a few bits. Okay, the bit rate is defined as the speed of transmission to transmit bit. Baud is also speed of transmission, but in terms of symbol per second. Okay, baud is also the speed of transmission. We calculate the speed of transmission based on how many symbols we are able to transmit. Okay, remember one symbol consists of a few bits. If it is a bit rate, it is shown as the speed of transmission to show how many bits have been transmitted in 1 second. But for symbol, how many symbols we have transmitted in 1 second. That's a speed also. Okay, the first one is amplitude shift keying. Okay, amplitude shift keying is the modulation process which change the amplitude of the carrier in accordance with the input variation. Okay, so assume that now, so this process is similar with the AM, but now the difference is the input is in terms of digital. So you have two possibility of input, logic 0, logic 1. So input cuma ada dua kemungkinan saja, logic kosong ataupun logic 1. Carrier, we use the carrier equation as VC cos omega naught t plus theta. Okay, so this is the carrier, and for the general equation of the ASK is equal to 1 plus input VMT multiplied with the carrier. Okay, so now the changes happens over here. If the input is logic 1, okay, VMT will become plus 1. If the input is logic 0, the VMT will become negative 1. So we just need to change the general equation to become like this. So if the input is logic 1, okay, we change the general equation over here, VMT to become plus 1. So the output gonna be 2 VC cos omega CT. But for logic 0, okay, the output gonna be, so we change VMT into -1. So it becomes 1 minus 1 becomes 0. 0 multiplied with anything is gonna produce 0. Okay. So this is the example to show the relationship input and also the output. You see that the input here is 1 0 1 0. So the output produced by ASK is something like this. For input logic 1 is gonna have a output signal. Input logic 0, no output. Input logic 1 with the output signal like this. Okay, so this is also known as the on and off keying, OOK. Okay, every time there's a logic 1, there's a output. Every time there's a input logic 0, there's no output. So it is like a switch on off. So that's why another name for ASK is also known as the OOK. Okay, so the baud rate and the bit per second is the same in this example because it is using 1 bit input. Okay, 1 bit input. And for the ASK, if you see from here, this is the waveform. Okay, the waveform of ASK. So we have the input over here, VMT, and the output is over here, ASK output. What about if we see the spectrum? We can find the bandwidth. So the bandwidth of ASK is 2 of the maximum input frequency. So if the input frequency, for example, up to 5 FM, that means the output bandwidth gonna be 2 times until the 5th harmonic, 2 times 5 FM. Okay, if the input is up to 5 harmonics, 5th harmonics, that means the output gonna be 2 times 5 FM, which is 10 FM. Okay, bigger bandwidth. So the general equation for the bandwidth is 2 FM. OOK can be done using multiplier. So how can we generate the OOK or ASK? Okay, so we can use the multiplier. Okay, like this. This is the multiplier. We multiply the digital input, digital code word, with the analog signal, analog carrier, to produce the output like this. Okay, so this is it for input logic 1, input logic 0, input logic 1, input logic 0, input logic 1. So it becomes on and off signal at the output. Okay. And for the receiver, so what happened in the receiver? So we can use a coherent detection for the receiver. So for coherent detection, okay, for coherent detection at the receiver, okay, coherent means that we are using carrier information to do the demodulation process at the receiver. Okay, that means we are injecting the carrier information in the receiver to do the demodulation process. So you see that here we still using the carrier information. Okay, we multiplied with the input. Okay, so here you're gonna produce a FLSB and also FUSB. Okay, and we use the LPF to remove the upper sideband, and we produce the original output with low frequency. Okay, so demodulation of OOK can be done using envelope detector, which is non-coherent. Okay, if you want to use a non-coherent, we can use the envelope detector or envelope demodulator. And what about for the bit error rate? Okay, for the bit error, for the bit error probability, okay, bit error probability PBE is calculated as 1/2 complementary error function of square root of EB over 2 and 0. So ERFC is a complementary error function, which we can find the values from the given table. Okay, so ERFC is a short term for complementary error function. Okay, so ERFC of Z is equal to 1 minus error function of Z. So what is Z? Z is this one, square root of EB over 2 and 0. Okay, so how to find this? We can use the table. Normally, when we do the face-to-face final exam, we give the students two tables. The first one is the error function table, and the second one is the complementary error function table. Okay, so how to read this table? Okay, how to read this table? Okay, so let's see the error function table. Here is the value of X. Okay, the value of input X, and over here is the value of output. Okay, the value of error function. So if, for example, if the input is 0.40, for example, okay, so if X is equal to 0.40, that means the output, okay, the output is 0.42839. If the input is 0.49, for example, the output would be 0.51167. Okay, another example. If the input is 2.90, okay, if the input is 2.90, the output, the error function output is 2.90. The output gonna be 0.99996. Okay, 9996. Similar with the complementary error function. If the input is 0.40, okay, the complementary error function output would be 0.51761. Okay, if the input is 0.49, that means the complementary error function output will be 0.48833. Okay, so what is X? So X is actually referring to this. Okay, everything inside the bracket is X. Okay, so that's why we need to solve the X value first. Normally we give you the value of EB over N0, so you need to find the you can find the X, then you can refer to the table. Okay, for example here, this is the example. Given EB over N0 is 0.32. Okay, given EB over N0 is 0.32. So find the probability of bit error. Okay, probability of bit error is equal to 1 over 2 complementary error function square root of EB over 2N0. Okay, so that means 1 over 2 ERFC of square root 1 over 2 EB over N0. Okay, we can rearrange the equation. So 1 over 2 ERFC square root of 1 over 2 times 0.32. 0.32 is given in the question. Okay, so from here we can find that it is ERFC of square root of 0.16, which is ERFC of 0.40. So ERFC 0.40, if you refer to the second table, okay, if you refer to the complementary error function table, you will find that it will produce 0.57161. Okay, but if you see from the error function table, it will produce 0.42839. Okay, so for example, we use the error function table, we take this value, okay, but we need to minus with 1 minus of this, then we can get the complementary error function table, complementary error function value. Okay, so you have two options. Okay, if you see from this example, the first method is it uses error function table. Okay, so if you want to use the error function table, that means we need to find the ERF 0.4 from the first table, from the error function table. We get this. Then we need to minus with 1. So we get this. Okay, this is if we refer to the first table. But if you refer to the second table, which is the complementary error function table, you will directly get this value. Okay, if you refer to the second table, which is this one, you will directly get this value. So if you ask me, better to use a second table, you will directly get the complementary error function value. Okay, and then what? So after you get this one, okay, it is not finished yet. Okay, it is not finished yet. So ERFC of 0.40, you will get the value 0.57161. Okay, so you change this to become this one, 0.57161, and it becomes remember, okay, so you already get this value from the table. Remember to multiply with 1 over 2. Okay, remember to multiply with 1 over 2, so you get probability of bit error would be 0.2858. Okay, so this is the probability of bit error. Okay, probability of bit error if we are using coherent detection. So this probability of bit error happens at the receiver if we use a coherent detection method. Okay, probability of bit error is the probability that the receiver will do error. For example, the transmitter transmit 101010. Suddenly, the receiver interpret this as 111010. So you see that there's error over here. So now we are actually want to calculate the probability that the receiver will do the error. Okay, so if for probability of bit error using a coherent detection, okay, for ASK, okay, probability of bit error for coherent detection using ASK for EB over N0 0.4, you will get 0.2858. Okay, and this is the probability of bit error at the receiver if we are using non-coherent. For non-coherent detection, okay, for non-coherent detection, we are not using the table. Okay, we can directly use the calculator. Okay, remember for ASK, non-coherent detection at the receiver, the probability of bit error calculation is equal to 1 over 2 exponent power of minus EB over 2N0. So exponent E, you can use from your calculator. From my calculator, I can use shift ln. If you press shift ln, you can make it as exponent. Okay, so let's try to do this. Okay, so you are given EB over N0 1.11. Find the probability of bit error for ASK non-coherent detection. So you can use the equation 1 over 2 exponent power of minus EB over 2N0. So you rearrange the equations and then you can put the values given, okay, 1.11, okay, multiplied with negative 1 over 2. So you get minus 0.555, okay. Try to use your calculator, okay, try to use your calculator, shift ln, and then press minus 0.555, you will get 0.5741 using your calculator. Okay, try use your calculator. For my calculator, E is equal to shift ln. Okay, and then after you get this using your calculator multiplied with 1 over 2, so you will get 0.2870. Okay, so this is the probability of bit error for ASK using non-coherent detection. Okay, so it's already 5 o'clock. Okay, it's already 5 o'clock. So I think we should stop here. And next week I will continue with frequency shift keying. Okay, frequency shift keying. So we still have a few slides. Frequency shift keying until QAM. Okay, I will continue next week. Okay, I will continue next week starting from FSK, and then I will move to chapter 5. Okay, so you can start open your QR code reader to take your attendance. Okay, I hope that nobody is feel asleep now, because you can take the attendance and then you can go anywhere you like. Okay, so open your QR code reader and then you can take the attendance. Okay, see you again next week.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Thank you, Doctor.
Welcome, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Doktor, saya tak boleh scan.
Siapa nama?
Muhammad Hamsyari.
Muhammad
Muhammad Hamsyari Hamizan.
Hamsyari. Okay, Hamsyari Hamizan. Okay, done.
Doktor, saya juga tak boleh scan.
Siapa nama?
Muhammad Joki. Nombor 11.
Okay, Joki. Okay, done.
Okay, thank you, Doktor.
Okay, welcome. Siapa lagi belum? Who else?
Muhammad Alif Aiman.
Muhammad Alif Aiman. Okay, done. Okay, settle.
Thank you, Doctor.
Okay, welcome. Who else?
Muhammad Amri, Doctor.
Muhammad Amirul Amri.
Yeah.
Amirul Amri Adam. Okay, done.
Thank you, Doctor.
Okay, welcome. Who else? Siapa lagi? Firdaus Fauzi mana? Where's Firdaus Fauzi? Okay, so one student's absent today. Okay, so that's all for today. Muhammad Firdaus, Alif Aiman, Izzah Izzani dah. Okay, tinggal Muhammad Firdaus Fauzi tak ada. Okay, so that's all for today.